Okay, so today we're going to talk about trig integrals. Now, obviously, you might be thinking at this point, we've already found integrals dealing with trig functions, and you are correct by thinking that, but however, here's what the idea of this section is going to be like. So the idea of this section is to use some of our trigonometric identities along with some strategies to integrate. So what you're going to notice is you're going to have trig integrals, except it's going to be trig integrals where we'd have to manipulate them in order for us to be able to find its antiderivative. So the way they are, it'll kind of be confusing. So we're going to manipulate them using trig identities, and these trig identities you learned from analysis. So I'm going to kind of give you the trig identities, but none of this should be new. So here are the trig identities to know. Now, some of them you'll use more frequently than the others, but the ones that we use often will be, obviously, this is pretty much the classic trig identity, sine squared x plus cosine squared x equals to 1. We have sine A times cosine B equals to 1/2 times sine of A minus B plus sine of A plus B. What else? We have sine A times sine of B equals to 1/2 cosine of A minus B plus, or sorry, it shouldn't be plus, it should be minus cosine of A plus B. And then we have cosine of A times cosine of B equals to 1/2 cosine of A minus B plus cosine of A plus B. Okay, and then we have, of course, our double angle identities, which this you should also remember. So these are the ones, these are trig identities that you need to know. If you don't know, you should try to memorize these because they're going to come in handy. Sine of 2x is 2 sine x cosine of x. And then for the double, for cosine, if you remember, there's 3 of them, which could be cosine squared x minus sine squared x, or equivalently, we could have 2 cosine squared x minus 1, or 1 minus 2 sine squared x. So if you remember in analysis, you definitely saw all of these. And in the last one, which we're probably going to use most often, are the half angle identities. Now, these may look slightly different than how you remember them, but they're not different. They're exactly what you learned in analysis. Oh, and I also forgot the double angle for tangent, so let's write that up here. Tangent of 2x is 2 tangent of x over 1 minus tangent squared x. Okay, so now let's continue on the half angle identities. We'll put them down here, which it'll be sine squared x equals to 1/2 times 1 minus cosine of 2x. And then we also have cosine squared x equals to 1/2 times 1 plus cosine of 2x. So like I said, if you look at these half angle identities, they may not look familiar to you, but if you recall, in analysis we said, look, sine of theta over 2 equals to plus or minus square root of 1 minus cosine of theta all over 2. So I claim that this and this are the same thing. Let's see how they are. Let's prove it. Let's square both sides. And when you square both sides, you lose the plus or minus, and this just becomes 1 minus cosine theta over 2. So this becomes sine squared theta over 2 equals to 1 minus cosine of theta over 2. And then we just use a simple substitution. You'd say, look, let theta over 2 equal to x. And if theta over 2 equals to x, what does that imply? Theta equals to 2x. So what happens is if I change the theta over 2 to x, I get sine squared x equals to 1 minus cosine, and theta becomes 2x over 2. So if I factor out a 1/2 from this, it'll look exactly like that. So sure enough, these are the half-angle identities. Now, why do we want to work with them in this form rather than this form? Because clearly, if you ask yourself this question, what would I rather integrate, this guy or that guy? And if you said this, then you need to kind of reevaluate what you're saying, because that's much easier to integrate. Okay, so that's why we want to work with these, because eventually we want to find the antiderivative. So these become so much easier to find the antiderivative of, because after all, once I distribute this 1/2, I could find the antiderivative of a constant, and I could easily find the antiderivative of cosine of 2x. So it just becomes so much simpler. Okay, now with that said, now that I gave you these identities, let's go for some of these strategies that I've been mentioning. So if we go to the back page, let's say we want the strategies right now for evaluating if something that looks like this: sine to the power of mx times cosine to the power of nx dx. So what we notice is sine and cosine have some powers, and so the question is, how could I find the antiderivative of this? And when you look at this, it looks a little messy. So we actually have some ways of manipulating this. So here's what we're going to say. There's actually 3 ways of looking at this. So let's first focus on cosine. If the power of cosine is odd, what we're going to do is we'll factor cosine of x and use cosine squared x equals to 1 minus sine squared x. Now notice how this is actually our Pythagorean identity. So what am I doing first? We are basically saying, okay, if this is odd, factor out a cosine. And if you factor out a cosine, the power becomes even, which then means if the power is even, I should be able to use this identity to write cosine in terms of sine. And when you do that, so that's the reason why we're doing that, is to write remaining factors in terms of sine. So let's kind of work out and see what happens here. So if I were to do that, so think of it this way: we have sine to the power of m times x times cosine to the power of 2k plus 1 x dx. Now, why is 2k plus 1 odd? Well, obviously 2, and we're assuming m and k are integers. So if k is an integer, 2 times k is obviously going to be even, and when you add 1 to it, it becomes odd. So this clearly, cosine has an odd power. So if cosine has an odd power, what are we going to do? We're going to factor out a cosine from this, which, how is that going to look? It'll be sine to the power of mx times cosine to the power of 2kx times cosine x dx. Because remember, what happened to that 1? Well, when I factor out a 1, it's here. And remember, when I multiply these, what do? I add the powers, which would give me the 2k plus 1. Now, what do I notice? This is cosine to the power of 2k. So I want to get this to look like cosine squared, so I could write it in terms of sine squared. So this is equivalent to sine to the power of mx. And I could rewrite this guy, I could rewrite as cosine squared x to the power of k. Now notice how that power of power is still equivalent to that, and don't forget the cosine of x dx. So now what I want to do is, now since I have cosine squared, I could write this as 1 minus sine squared. And if I do that, this becomes the integral sine to the power of mx times 1 minus sine squared x to the power of k times cosine of x dx. Now, hopefully at this point, you should look at this and say, how nice is this? I could easily find the antiderivative of this through u sub, because what are you going to say? You're going to say let u equal to sine of x. And why do we like that? Because when you let u equal to sine of x, then what's du going to be? Du will be cosine of x dx, which then you could use u sub and finish this off. Okay, so hopefully you see what's going on. So what are we saying here? If the power of cosine is odd, factor out a cosine, then it becomes even power, and then we could write the rest in terms of sine. Then we could proceed to solve this integral using u substitution. Okay, so the next method is, well, what if the power of sine is odd? And if you should already know by now, if the power of sine is odd, we're pretty much doing the same thing. So if power of sine is odd, instead of factoring out a cosine, now we'll factor out a sine. So we would say factor sine of x and use sine squared x equals to 1 minus cosine squared x to write remaining factors in terms of cosine. And that will allow you to pretty much use u sub again. So basically, here's what we're saying. Now we're going to have the integral of sine to the power of 2k plus 1x cosine x dx. So what you could do now is you could factor out a sine. So if I factor out a sine, this will be sine squared x to the power of k cosine x sine x dx. So I went ahead and remember from here, I went from this step, where was it? This step to that step. I just went ahead from here. I factor out a sine, and then this was a sine to the power of 2kx, and I just wrote it as sine squared x to the power of, and this is a k. So that's what we have. So then once we have this, we could say, look, sine squared is the same thing as 1 minus cosine squared x to the power of k times cosine of x times sine of x dx. So once again, once you get it to this point, now you could use u sub, except now you'd say let u equal to cosine of x, and then of course du will be negative sine x dx, and then you could finish this off on your own. Okay, and then you could use then you could easily integrate this. Okay, so the question then becomes, well, what if none of the powers are odd? Because see, once one of the powers are odd, it's really nice and convenient. So if then the last case is if both sine and cosine have even powers, then use the half angle identities, which basically they're the sine squared x equals to 1/2 1 plus cosine 2x, or it's 1 minus, and then cosine squared x equals to 1/2 times 1 plus cosine of 2x. So this is, remember, this is a minus. So why do we like this? Because look, when the powers are even, then what happens is when we use the half angle identities, we lose the power, or the power is cut in half. And see, I could easily find the antiderivative of this, but this one I can't. And so remember, if this is sine to the 4th x, I would have to use the half angle identity twice, right? Once to get it to become sine squared, and another time to get it to become, or not sine squared, once to use it to become cosine squared, and another time to make it cosine to the power of 1. So just keep that in mind. If both are even, you can't use tricks A and B, so you'd have to use the half angle identities, okay? So that's kind of what's going on here with these three methods. So let's actually work on a few examples so you'll kind of see how this works out. So for example 1, we're going to say evaluate the integral sine to the power of 5x cosine squared x dx. So if you take a look at this right away, I'm looking for my odd powers. Now look, if both of them are odd powered, it doesn't matter which one you factor. But in this case, sine is odd. So what I'm going to do is I'm going to say, look, factor out a sine. So if I factor out a sine, this becomes what? Sine to the fourth x, cosine squared x, sine x dx. And then this is equivalent to what? The integral of sine squared x, quantity squared, cosine squared x, sine x dx. Right? I just got this to look like that. So now I could replace sine squared with 1 minus cosine squared x, quantity squared, cosine squared x, sine x dx. So when you look at this, it looks messy, but don't worry about it. It's actually going to become a lot cleaner. So now we're ready to use u substitution. So we're going to say let u equal to cosine x. Then what's du? du is negative sine x dx, which means negative du is equal to sine x dx. So let's actually finish this off. So what does this become now? This becomes the integral of 1 minus u squared, quantity squared, times u squared. And then the sine x dx just becomes, so let's put a negative out front, and it'll be a du. So now before I could integrate, I'm just going to have to multiply these out, which that's not a problem, right? So what's 1 minus u squared going to be? This will be 1 minus 2u squared plus u to the fourth. That's what this is. And then if I distribute the u squared, I get u squared minus 2u to the fourth plus u to the sixth du. And now I could integrate, which gives me negative 1/3 u cubed plus 2/5 u to the fifth minus 1/7 u to the seventh. Now remember, I distributed this negative at the same time as I found the antiderivative, plus c. So now what I need to do to finish this off, I just plug back into u cosine. So this becomes negative 1/3 cosine cubed x plus 2/5 cosine to the fifth x minus 1/7 cosine to the seventh x plus c. And there you have it. Okay, so it's not too bad. You just kind of have to manipulate it as needed. Okay, so let's move on to example 2. So for example 2, we're going to say evaluate the integral of sine to the power of 4x dx. Now, here's the problem. See, I have sine to the power of 4, and I don't have any cosine. So the only trig function I have is to an even power. So guess what we said? We have no choice but to use the half angle identity. So if this is sine to the power of 4x, we could look at this as sine squared x quantity squared dx. And we said sine squared is equivalent to 1/2 times 1 minus cosine of 2x quantity squared dx. Okay, and then let's square this out because parts of it will be able to integrate. So this 1/2 becomes a 1/4, and let's pull it out front. And what's 1 minus cosine of 2x quantity squared? It'll be 1 minus 2 cosine of 2x plus cosine squared of 2x dx. Now look, let's take a moment and look at this. I could find the antiderivative of that. I could find the antiderivative of that. That guy I can't find the antiderivative of. So guess what? To be able to go any further, or to be able to find the antiderivative of this, I could use the half angle identity for this again. So what does this turn into? Now think of it this way. Before I substitute here, here's what we know. We could say, look, if cosine squared x is equal to 1/2 times 1 plus cosine 2x, then clearly we could say then cosine squared 2x. If this is x and that becomes 2x, then if this is 2x, this should be 1/2 times 1 plus cosine of 4x. Okay, so that's what we're going to do. So if we have that, so now I could continue that on here, which this is 1/4, the integral of 1 minus 2 cosine of 2x, plus that becomes 1/2 1 plus cosine of 4x dx. Now look at how nice this is. So, you know, I don't know, I think this stuff is like awesome, you know, the way it works, the way it is, you know, because at first you're like, wow, I can't find the antiderivative of this, and then next thing you see, it kind of cleans up so much. So this becomes what? 1/4, 1 minus 2 cosine of 2x plus, let's distribute this 1/2, it becomes 1/2 plus 1/2 cosine of 4x dx. And see, I could combine that 1/2 with that 1. So let's do that right here. Let's just call that 3/2, and let's get rid of that. And then the rest I can't do anything with. So now let's find the antiderivative. This is 1/4 times 3/2 becomes 3/2 x, and then minus the antiderivative of cosine becomes just sine, but remember of the 2x, so it'd be sine 2x, and then because of that 2x, I would have to remember the chain rule. The derivative of 2x is 2, so I'd have to put a 1/2 here. So that 2 and the 1/2 cancel out, it just becomes a 1. Okay? And then plus, what happens here, the antiderivative of cosine is also sine of 4x, but remember I also need to divide this by 4 because the derivative of 4x is 4, so to kind of undo that, it'll have to be 1/2 times 1/4, which becomes 1/8, and then we'll say plus c. Okay, so once you have that, distribute the 1/4, and then we're done. So this becomes 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus c. And there you have it. We just found the antiderivative of a trig function that's even. Okay, so just keep that in mind. When you have all even powers, the odd powers are easier to work with, obviously, but if you have even powers, it's not that we can't. We'll use the half angle identities. Okay, so with that said, now what I want to do is I want to go on to the last types of strategies, and then we'll do a couple more examples, and then that'll basically do it. So we want to talk about the strategy for evaluating the integral of tangent to the power of mx secant to the power of nx dx. Okay, so then once again we're going to keep track of the powers again. So for the first method is if the power of secant is even, so we're basically saying n equals to 2k and k is greater than or equal to 2. So what are we saying here? If it's even, but in a sense where it's 4, 6, 8, so what you're going to do is, so remember, we're talking about even, and it has to be greater than 2. So what if it's secant to the 4th, secant to the 6th, 8, and so on? The reason why we want it to be greater than 2 is because we're going to factor secant squared x. Now hopefully you see why we want to factor out a secant squared x, because look, we're trying to use the u substitution again. And why do I care about secant squared? Because look, when I let u equals to tangent, what's the derivative of tangent? It's secant squared. So that's why we want to factor out a secant squared and not just a secant. Okay, so then what happens is when you factor out a secant squared, whatever is left, you want to write everything else in terms of tangent. And if you remember, we have a trig, one of those trig identities from last year where secant squared x is equal to 1 plus tangent squared x, to write the remaining factors in terms of tangents. So just to kind of show you what's going on, here's what we're saying. We're saying, look, we have tangent to the power of mx, secant to the power of 2kx dx. And so once again, we're assuming secant is even, and it's a number greater than 2. So it's 4, 6, 8, something like that. So this will be what? The integral of tangent of to the power of mx times secant squared x to the k minus 1, and this would be secant, and this should be k minus 2, secant squared x, right? Because I factored out 2 of them, okay? So no, this should be a k minus 1, sorry, not a 2, because 2k times 2, so if I just multiply this 2, what do I get? 2k minus 2, and when I multiply the secant squared back, and when I add the minus 2 and the 2 together, I get secant to the 2k again, so that should be k minus 1 dx. So once we do that, then I could write secant squared, so this becomes the integral of tangent to the power of mx. This would be times 1 plus tangent squared x to the k minus 1 times secant squared x dx. So then from this point on, we're ready to use u sub, and you'd say let u equal to tangent of x, and clearly du will be secant squared x dx. Okay, and there you have it. So you could use u sub, but remember, hopefully you understand why we want to factor out a secant squared, okay? Because when you let u equal to tangent, the derivative of secant squared. If you factor out a secant, that won't be good enough, okay? Now, if the power of tangent is odd, so what we're saying is if m equals to 2k plus 1, right? That's what it means. That means the power of tangent up here, which we're calling m, is 2k, that's odd. Then we're going to factor a secant x tangent x and use your trig identity, which is tangent squared x equals to secant squared x minus 1, to write remaining factors in terms of secant. And then you could use u sub, and you'll let u equal to secant, because what is the derivative of secant? It's secant x tangent x. So that's why we care about factoring out a secant and a tangent, because through the u sub, when I let u equal to secant, the derivative is just that. So what we're going to say is, if we were to write this out, you'd get tangent to the power of 2k plus 1 x secant to the power of nx dx. This becomes, if I factor out a tangent, that becomes just the integral of tangent of squared x to the power of k, and then this becomes secant to the power of nx, and then there's a, or actually I'm factoring out a secant, so this would be n minus 1, so it'll be secant x tangent x dx. Because look, what did I do here? I factored from this, I factored out a secant and a tangent, so this became a secant to the n minus 1. This one, tangent lost its 1, and I wrote 2k as squared to the power of k. So that's what we have. So then, after you have this, you'd grab this and say, well, tangent squared x is equivalent to secant squared x minus 1, quantity squared, secant to the power of n minus 1x, secant x tangent x dx. And so from here, you'd let u equal to secant of x, and then du would be secant x tangent x dx, and then you could finish that off. So let's look at a couple of examples, and then that'll basically finish off this section. Okay, so for example 3, we're going to say find the integral of tangent to the 5th theta secant to the 7th theta d theta. And so what do you notice? Right away you notice that tangent is odd. So if the power of tangent is odd, and by the way, the power of secant isn't even. If it was even, you could have done part A of the strategy, but since this is odd, then we know that we want to factor out a secant and a tangent. So if I do that, this becomes tangent to the fourth theta, secant to the sixth theta, and then we have what? Secant theta tangent theta d theta. And then this tangent to the fourth is equivalent to what? Tangent squared theta quantity squared. And what we're going to do here is now I could replace tangent squared in terms of secant squared theta minus 1. So this becomes secant squared theta minus 1 quantity squared, secant to the sixth theta, secant theta tangent theta d theta. So now I'm ready to use u sub. So we would say let u equal to secant of theta, which then du is secant theta tangent theta d theta. So now we're ready to substitute. So this becomes u squared minus 1 quantity squared times u to the sixth and then du. So once again, this becomes so much easier. All I need to do is just multiply everything out. And if I multiply everything out, what do I get? It becomes u to the 10th minus 2u to the 8th plus u to the 6th du. Okay, so now we could find the antiderivative, which becomes 1 over 11 u to the 11 minus 2/9 u to the 9 plus 1 over 7 u to the 7 plus c. And once you do that, now you could plug back in for u, which is 1 over 11 secant to the power 11 theta minus 2/9 secant to the power of 9 theta plus 1/7 secant to the power of 7 theta plus c. Okay, so before we do our last example, what I want to do is I want to mention a couple of integrals that we should keep an eye out for. And the two integrals are, so some other cases may require these integrals. And see, we've actually solved these integrals by use substitution, but you could just use this right away. So tangent of x dx, the integral of tangent of x dx is just ln of the absolute value of secant of x plus c. And see, we've done this before. You could write tangent as sine over cosine, and you could use u sub. But we've used this so much where you could just use this result right away. You don't need to show me why is it like that, okay? And then also the integral of secant of x dx is the ln absolute value of secant of x plus tangent of x plus c. So these two integrals, you might come across these. So if you see the integral of secant, you can just go ahead and use this and you can move forward, okay? So our last example will be the following. We have the integral of secant cubed x dx. So here's what we're going to say. I'm going to say, look, what's the problem here? We know if that the power of secant is even, then I could factor out a secant squared from this. But no, since the power of secant isn't even, I can't use that trick that we learned, okay? And in fact, there is no tangent anyway here for me to use the trick. So we have to find a different way of doing this. So one thing you could do is you could say, look, why don't I think of this as, you could rewrite this as, and hopefully, I mean, it's not obvious, but once I write it out like this, hopefully it'll be more obvious to you. Write it like that. So what did I do? I wrote this integral as a product. And whenever you're trying to find the antiderivative of a product of two functions, what should you use? And the answer is integration by parts. So when we look at this, see, I know that the antiderivative of secant squared is tangent. So clearly I want to let u equal to secant of x, and then dv equal to secant squared x dx. And what does that mean? du will be secant x tangent x, and v will be tangent x, and this should have a dx, right? So now let's use this. So what do we have here? We have the integral of secant cubed x dx equals to the integral, or equals to uv, which is secant x tangent x minus the integral of v du, which it'll be what? Secant x tangent squared x dx. Okay, so now what is it that we notice here? We could say, look, what I could do here is I could grab tangent and write it in terms of secant, because what could I say? Tangent squared is the same thing as secant squared x minus 1. So this equals to secant x tangent x minus the integral of secant, and if I distribute the secant, what does that become? Secant cubed x minus secant x dx, which then I could split this integral up, which becomes what? Secant x tangent x minus the integral of secant cubed x dx, and with this minus and that minus, it becomes a plus integral of secant x dx. And look at how nice this is. This one we know the antiderivative of. I just gave that to you, didn't I? So that antiderivative will be ln of the absolute value of secant plus tangent. Now this guy, hopefully you notice something. Look, isn't this what we're trying to find the antiderivative of? So in other words, this, all of this is equivalent to that. So if we go down, let me kind of take a couple more minutes and just do this. So we're saying secant of x tangent of x minus the integral of secant cubed x dx plus this, we said we have the antiderivative. I just gave that to you, which will be ln of the absolute value of secant of x plus tangent of x plus c. Now look at what happens. The only integral left is this guy and that guy, which isn't that what we're trying to solve for? So this is kind of like that integration by parts problem we did in last section, where example 2, remember we had to kind of, it was an infinite integral or infinite integration by parts if we kept going. Same thing is going on here to some extent. So what I've noticed is, what are we claiming? The integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant cubed x dx plus ln of secant of x plus tangent of x plus c. So what I could do now is add the integral of secant cubed x dx to both sides, which that then gives me what? 2 integral of secant cubed x dx equals to secant x tangent x plus ln of absolute value of secant of x plus tangent of x plus c. And all I need to do is divide both sides by 2, which then the integral of secant cubed x dx equals to 1/2 secant x tangent x plus 1/2 ln of absolute value of secant x plus tangent x plus c. And there you have it. So this last example I did was not, is nowhere near easy or a moderate problem. It is difficult, so it takes some time. So you'd have to be very cautious when proceeding with this, especially when it comes to seeing that, hey, I could rewrite this as that, and then let's use integration by parts. And even when you do that, you have to manipulate it some more. So this one's a tricky one, but hopefully it makes sense once I kind of showed you how to solve this out. Okay, so that basically takes care of this section. Remember, you're just literally trying to manipulate these trig integrals so that you could find easy ways of finding their antiderivatives. Okay, so make sure to ask me any questions if you have any when I see you in class. Enjoy the problems.